Good evening, ladies and gentlemen, and welcome to the 2025 Darwin College Lecture Series on Codes. It's wonderful to see this lecture theatre full, and for the benefit of those who are in our overflow, or indeed especially those who choose to watch the Darwin College lectures on the Darwin College YouTube channel, I'd like to welcome them as well. Last year's lectures, we're rather proud to say, were viewed by over 220,000 people on YouTube. A great achievement of which the college is very proud, although I have to say I'm rather glad they didn't all try and come into this lecture theatre, otherwise we would have had a different kind of problem. This year we are holding the 40th series of Darwin College lectures, as I'm sure many of you know, which appropriately began 40 years ago with the topic of origins. It was a lecture series orchestrated by our emeritus fellow, Professor Andy Fabian, astronomer, and under his leadership of education and research at the college, the lecture series were founded, and I'm delighted you're here tonight, Andy. Our very first speaker in the series back then was Lord Martin Rees, the Astronomer Royal, an honorary fellow of the college, who of course talked about the origins of the universe. Since then, we've been fortunate enough to have 320 Darwin College lectures from a distinguished and wide-ranging selection of scholars, including the mathematician Stephen Hawking, lawyers Helena Kennedy and Sherry Booth, the politicians Shirley Williams and Oliver Letwin, himself a Darwinian, the scholar of linguistics and philosopher Noam Chomsky, Archbishop Desmond Tutu, and last year Simon Sharma, together with many others. This year, of course, is no different, and over the next 8 weeks we've got another series of wonderful speakers, including our speaker tonight, Professor Simon Peyton Jones, a prominent computer scientist known for his influential work in programming languages and functional programming. He's best recognized, as I'm sure many of you will know, as one of the key designers of the Haskell programming languages. Unusually, he straddles both teaching, a passion for teaching, a passion for engaging future generations in the importance and values of computing, together with being both an academic and working in the private sector in industry. He graduated from Trinity College here at Cambridge, went on to become a lecturer at the University College London, and then a professor at Glasgow University before joining Microsoft Research here in Cambridge. He's currently an engineering fellow at the company called Epic Games, and is deeply, deeply involved in computing education at schools, where he works particularly with a grassroots organization called Computing at Schools, encouraging and trying to transform the way computing education is taught in this country. He was in 2016 elected as a Fellow of the Royal Society, appointed a distinguished honorary fellow of the University of Cambridge Department of Computing Science, and awarded an OBE in 2022 for services to education and computer science. Perhaps one of his most unusual accolades was being jointly awarded the 2014 Association of Computing Machinery Most Influential Paper Award for a paper or a publication that was entitled Scrap More Boilerplate, Reflection, Zips, and Generalized Casts. So, if you want to know more about that, and be enlightened, please join me in welcoming Simon Peyton Jones to give the first lecture.
Very good. Well, good evening, Cambridge. I shall not, I'm afraid, tell you anything about generalized casts. So much of what we do is, involves complicated digital technology, and yet all of it rests on something quite simple, quite beautiful, and quite elegant, and that is just bits. So today, I'm going to take you on a little worm's eye journey, eschewing the bird's eye view of all this stuff, a worm's eye journey to give you, what I'd love to give you is a sense of the joy and beauty and elegance of some of the underlying stuff that makes all of our devices work. In the hope that if you get some sense of what's going on there, you may be in a position to make better informed judgments about the ubiquitous technology that surrounds us. So I'm going to do this in the form of a little journey in several episodes, and the little journey is both an intellectual journey, one that I hope that you will share with me, but also a personal journey. It has some sort of connection to my own personal life. So I'm going to start with me. This is me age 6-ish, but actually the story relates to me age about 10. My school teacher, Mr. Footner, said to me, look, Simon, a man, he sent me away this problem for the holidays. A man goes into a bank, he comes in every day, he's always in a hurry, he's always angry, he wants a sum of money between £1 and £1,000, always an exact number of pounds, and you figure out a way to take 10 envelopes and put sums of money in each envelope. So when he comes, he says £673, and you just go flick, 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 give him some envelopes, all done, right? What is in the envelopes? So I went away for the holidays, and what did I do? Well, I would like to say I did exactly this. I'm going to give you the short path. The guy, suppose he wants for £1, we better have an envelope with £1 in it, right? Suppose he asks for £2, well, I could have another envelope with £1, but it might be better to have an envelope with £2, right? And now I can do £3, just putting both of those envelopes. Now, what about £4? Well, I better have an envelope with £4 in it, and now I can do 5, 6, and 7, right? All of them, right? So now I need an envelope with £8. And you can see how this is going, right? That each time, one more envelope gives me access to 2, 4, 8, 16, 32, and so forth. It turns out 10 will do up to 1,024. What my teacher had forced me to do, he had forced me to invent the binary number system without telling me that that's what I was doing. Who is a school teacher in here? Hands up, school teachers. 1, 2, 3, 4, 5. You are my heroes and heroines. Every day you are like Mr. Foot. This is 55 years ago I'm telling you this story. In 55 years' time, one of the children you've met today will be telling a story about what you did today. So thank you so much, school teachers. You really, I salute you. Please do more of it. I've got children at school at the moment, so I've got an intense, passionate interest in this. So here we are. If you replace the ticks and the crosses with ones and zeros, you get what those of you who know the binary number system will see as binary, but let me just give a quick look. So in the decimal number system, the one number thing we're all used to, 4,792, we know that the 4 is thousands, the 7 is hundreds, the 9 is tens, and the 2 is units, right? Well, in the binary number system, it's just that the first digit here is going to be 16s, then 8s, then 2s, just those envelopes, remember? But each of the digits now, instead of being 0, 1, 2 up to 9, each of the digits, the binary digits, and bit is just short for binary digit. Each of the bits is just 1 or 0. That's all it is. So binary, incredibly simple, and Mr. Footner had forced me to invent it. And then he showed me another insight, which is that the same number, 5, I could write that down as 5 in decimal, or as 101. So in some sense, the 5 that I was used to in decimal and the 101 are both codes that represent some philosophical essence of fiveness. Do you see what I mean? It's just 5 as a little symbol. It's pretty arbitrary. It's just a code for the thing itself. And once you've learned these other number systems, you realize there are many codes for the same thing. Okay, so here is a definition of code from the Cambridge course, the Cambridge Dictionary. System of words or signs used to represent a message in secret form. So I'm going to de-emphasize the secret bit just to represent something else. So code represents something, right? And we've just seen that a sequence of binary digits, bits, can represent a number. But as you will almost certainly know, bits can also represent things other than numbers. They can code for things other than numbers. So here is a bit can code for text. So here's a little table giving a little coding. So A is represented by the number 65, which is itself represented by bits. So, here I is represented by something, I is by 105. So this sequence, 83, 105, 109, that's my name spelt out in code. Right? It's just a little arbitrary code, and each of those numbers itself is represented as binary, so now I can represent my name just written down just with bits, right? But bits, of course, can represent not just text, but anything else. Well, what about music? Oh, music is a little waveform, right? If we measure the height of the waveform, if we take, let's say, 40,000 samples a second and see how high the waveform is each time, each of those heights is a number, that is a binary bit pattern, then we've got 40,000 little bit patterns per second. Just store all of those, that's your sound, right? Then all you've got to do to play it back is to make a loudspeaker move around 40,000 times a second in response to those numbers. Easy, right? It's just bits, just bits. That's what's in your MP3 file. Same with pictures, of course. You'll have heard of pixels. You'd have seen pixels. Sometimes pictures become pixelated. You divide the thing into grids. Then you have the amount of red, amount of blue, and amount of green. That's interesting that 3 numbers will represent the color of a thing. Many people know that, right? So red, blue, and green, 3 numbers per pixel. Now you can represent a whole picture. How can you represent a movie? Just lots of those. So everything is bits. All of this stuff, all of human creativity, writing, drawing, performing, everything, it's all representable as bits. That doesn't suck out the creativity. It's just saying we represent that creativity in bit form. And once we do that, we take this for granted, but it's so remarkable. Once we do that, then we can do to those same bits, we can use the same set of techniques. So if we want to store them on a computer, or send them over a wire, or encrypt them, or compress them to take up less space, all of those things can be done rather independent of what the bits are representing, right? So it's very powerful that all of this stuff just gets represented in the same way. There we are. So that's episode 1. All right? Now, we just need to say a little bit about scale, though. So scale matters. A few bits, not so impressive. Lots, but we have lots of bits. So a byte is 8 bits. Kilobyte, 1,024. Why 1,024? Well, remember that little table? That was 10 bits worth of stuff, right? So then a megabyte, gigabyte, terabyte is 1,000 times, well, 1,024 times each of those. So by the time we get to a terabyte, we're getting to quite a lot. But a terabyte these days isn't very much. This is a terabyte disk drive. It's incredibly light. It comes in my PC, and it's how much is a terabyte, I wonder? But it's very cheap too. Now this is a few tens of pounds. So how much is a terabyte? Let's try this. Here's the Bible, right? How many copies of the Bible will fit in this disk drive? So let's see. Philip Lockley, how many pages in the Bible? Where are you? Oh, there he is. Oh, 1,000 odd or something. Maybe, it depends on the Bible, but it's all the same Bible, but maybe it depends on the print. So let's see, 1,000 odd pages and 700 lines, maybe about 700,000 words in a Bible. And then each word is maybe about, I don't know, a certain number of letters, and each letter takes 1 byte. So I'm going to guess around 5 million bytes for a Bible, right? 5 megabytes. How many 5 megabytes are there in a terabyte? Anyone? 200,000. All right. How tall is a stack of 200,000 Bibles? Here it is. 200,000 of these. How tall? Oh, it's 5 centimeters each, like 20 meters. My guess was 10 kilometers, right? So next time you're in an airplane flying along at 36,000 feet, that is 10,000 meters, and you go past a stack of Bibles, you can think all the way to the ground fits in this disk drive. And that's before you compress them, right? A Bible has quite a lot of redundancy. It says God a lot. You can maybe make that a bit shorter, right? So maybe you could fit 10 times that, probably, by a bit of compression. That is a lot of Bibles, and we just take it for granted, don't we? A terabyte, hey, look, just, what's the, it's a big deal. Scale matters. Okay, end of episode 1. Episode 2, we talked about information, and we're going to talk about computation. Second story from my youth. I'm now a bit older, but also at school. So I think I'm about 12 or 14, and I learn about this game called NIM. NIM is a 2-player game. You play it with piles of matches, let's say 3 piles, and you start off with some random amounts in the piles, and in each move, one player removes any amount of matches from one pile. And then the other player does, and then the first player does. Your goal is to remove the last match. And it turns out that it is possible, if you can choose who starts, that you can always win. And to a 12-year-old boy, that possibility is enormously attractive. It motivates a good deal of study. Now, I'm going to cheat by showing you how to do that, because I really want you to understand some of this. It's so easy, right, when you see it. Right, so here's the idea. So here's 3 piles. They've got 5, 9, and 2 matches in each. Write the size of the pile in binary. That's what I've done here. So 5 is 101, 9 is 1001. Now, vertically in the columns, just look at each column independently. If there's an even number of ones, put a 0 at the bottom. If there's an odd number of ones, put a 1 at the bottom. That's easy enough. Any person could do that, right? So these ones are odd. The first and last ones are even. Good. Now, your goal is, when it's your go, you're going to do something that means that you can hand over the game with all zeros on the bottom line. That is, all the columns out have an even number of ones. How do you do that? Well, let's suppose it was like this. The idea is this. You're going to pick the leftmost one in the bottom row, and then you're going to pick the pile, at least one pile here, 9, that has a 1 in that column. So the third column, right? Now, so you're going to turn that 1 to a 0. And if you turn that 1 to a 0, then you can turn any of the other bits in that number to 1s, and you'll still get a smaller number. Like saying, if you've got 700 and blah, 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 if it turned into 600, you could go 699. You could do anything to the rest. OK, so we're going to do this. And we're going to do that in such a way, we're going to flip bits here to make the bottom row all zeros. That's not hard, is it? And then you can say, oh, now, this pile here now has 7 matches in it, because that's the binary code for 7, 0, 1, 1, 1. That's the binary code for 7. Right? So you remove 2 matches. Right? It did have 9. You make it 2. You hand it over with all zeros. Your opponent has got all zeros. It turns out they are forced to give it back to you with a 1 somewhere in the bottom row. So it turns out, you see, that you can always hand it over as all zeros, as I've shown you, and they can never hand it back to you as all zeros, and the number of matches decreases, and when you take the last match, it's all zeros. Your opponent couldn't possibly take the last match, because then they'd be handing back with all zeros. Bingo. Proof by induction, but actually quite intuitive. You're going to win this game. Don't you think that's amazing? I thought that was quite, this weird, rather academic, dry binary stuff turned out to help me win a game. In a very non-obvious way. Without this, you wouldn't have a chance of winning at NIM, not every time. So I wanted to, now, there's a bit of a point to this as well, which is that what I'm doing here is I'm computing with bits, right? Up to now, I started with the bits were sort of passive. Here, I'm being a bit more active. This business of counting up the 1s and 0s and saying, is it even or odd? That's called taking the exclusive OR of those bits. And this exclusive OR function was invented by this fellow, George Boole, who is enormously influential in logic initially, but computer science now. And I've given you the little table for exclusive OR. For exclusive OR takes 2 inputs, A and B. And if there's an odd number, if like 0 and 1 and 1, 0 produce 1. But if it's an even number, 0, 0, 1, 1, they produce 0. That's it for exclusive OR. Incredibly simple. But Boole was clever enough to say this incredibly simple thing might actually be important. So we're doing a bit of computation over these bit patterns. We're going to write a computer program to do it. And really, this is all computers do. Computers are simply lots of bit pattern shoveling. They just take bits off that disk, they scramble them around about, and they shove them back. So they're doing lots of this stuff. That's computation. That's what computation is. OK, end of episode 2. We talked about information, communication, and computation. We're going to talk about communication. All right. Now, it's going to involve bits, of course. Here is Alice and Bob in a crowded Darwin lecture theatre, and their eyes meet across the room. They've never met before, so they share nothing in common, but they would like to have a private conversation. But the room is sadly full of nosy people. Are you nosy? Probably, right? So Alice and Bob would like to have this conversation. How can they do so? If only they had a secret key, they could encrypt their conversation so that the others could not read it, right? So I think, I'm not going to describe encryption, but I think you can guess that if a secret key is just a number, they could add 27 to every character of their message. That might be an easy one to crack, but there are lots of harder ones. So you need a secret key that you share and the nosy people do not. So the question is, could Alice and Bob have a public conversation that everybody can hear And at the end of the conversation, they share a secret key that only they know and the nosy people do not. Think about that for a moment. Does that not sound impossible? Do not even bother to try. Yeah? Sort of nod. Look as if you are sort of convinced that it is a difficult thing to do. Because I'm going to show you how to do it, so I want you to feel that you are, okay. So, Diffie and Hellman, you see, these chaps, were not as discouraged as I was, and they figured out how to do it. And moreover, it's not just they figured out how to do it, we are doing this every day. If you bought everything on e-commerce today, when your web browser shows that little padlock, it is doing Diffie-Hellman key exchange. And I'm going to show you what it's doing. Are you ready? Okay. So Alice decides on a number, n. I'm going to call it n and put it in orange because it's public. She shouts it out. Everybody knows n, right? She makes up a secret number, A for Alice, that only she knows. And she does not shout it out, but what she does do is she multiplies n by itself a times and shouts that out. And mathematicians, so it's n times n times n, a times. With mathematicians write n with a funny little superscript a here. But it just means n times n times n, a times. Good? Okay? Bob does the same, but he does this with a secret number b. Okay? So now everybody knows n to the power a, which is here, my example, n is 5 and a is 2, Alice's secret number is 2. N to the power of 2, n times n is 25. And b is 3, and 5 times 5 times 5 is 125. Good? So everybody knows those two. Very good. Now what happens? Finally, Bob computes n to the power a, which is public, right, to the power of b, multiplied by itself b times. So he's computing n times n times n, a times, which Alice shouted out. He multiplies it by itself b times. So how many n's have I got in this row here? Master, how many n's have I got in this row here? N, a times b, very good. A times b, n. Meanwhile, Alice computes n to the b, which Bob shouted out, and multiplies that by itself a times. So she too has n multiplied by itself a times b times. Very good. All right. So now, of course, the answers are the same. So here we are, n to the power a to the power. They both get 15625, and that's their secret key. Now, of course, this being a Cambridge audience, you're all thinking, Simon, there's a loophole in this very clever algorithm, right? Because after all, the nosy people know n, and they know n to the power a, so how hard can it be to work out a? They know n. They know n times n times n times n, a times. Is it hard to work out a? Not very. You could just try a equals 1, a equals 2, a equals 3, which is called the British Museum algorithm for some reason. I don't know why. It seems a bit rude to the British Museum, but I think it's because they enumerate a lot of objects. An easy way to speed it up is to write this little table here, and you could say, well, let me start halfway down. And then if Alice shouted out a number that's bigger, I'll look further up in the table. Otherwise, I'll look further down. And you can halve each time. That's called binary search. Another little nod to binariness. But it turns out, so this is completely hopeless, right? But Diffie and Hellman had a secret plan. Here is their secret plan. They used clock arithmetic. So clock arithmetic means this. Normally when you add 2 and 3, you get 5. If you add 11 and 1, you get 12. But on clock arithmetic, when you go past 11, when you're in clock arithmetic in the 12 world, you go back to 0. So 11 plus 1 is 0. And what is it? I've got 10 plus 4 is, click, click, 4 on from 10 is 2. Right. Let's do one that isn't here. What's 9 plus 5? 2. Very good. 9 plus 5 is 2. Yes, very good. Okay. And 5 times 5? Well, that's 25. Oh, now you have to think a bit harder. Do I have to go 5 plus 5 plus 5? No, you can do this simple trick, which is to say, do 5 times 5 without thinking about this clock business, get 25, and then take the remainder when you divide by 12. Because after all, that means you've gone round the clock once, round the clock again, a little bit further. Easy, right? Remainder when you take 12. Now, mathematicians call this mod 12. Take the number mod, that just means it's a complicated way to say, or sort of impressive sounding way, you can impress your friends, complicated way of saying, take the remainder when you divide by 12. Right. It's called mod because mathematicians call this not clock arithmetic, which is very primary school. They call it modular arithmetic, which sounds like professor stuff. Okay, now then, all we do is we do exactly what I showed you, but at every step, you take the remainder when you divide by k. What is k? It's just another number that Alice shouts out. So it's public. Everybody knows it. Everybody knows n. Everybody knows k. Everybody now knows, everybody now knows n to the a mod k, because at every step you take mod k. Yeah? So nothing hard is going on here. In fact, it's easier, but n to the a to the b is a very big number. These mod things are always smaller than k. After all, it's the remainder when you divide by k. Very good. So each step remains very simple. Good. Now then, here's the amazing bit, that can you now figure out, if you know n, and you know n to the power a, can you work out a? Answer, no. Well, answer, yes, but very slowly. So here is the same table, right, with 5 to the a mod 11. Here, instead of using 12, I've used 11, because 11 is prime, and it just turns out that prime numbers work better as the k stuff in this kind of algorithm. So here, for 5 to the a mod 11, it's all over the place. 5, 3, 4, 9, 1. No rhyme or reason to that, right? So this halving algorithm doesn't work at all. And in fact, it turns out that, so you can still do the British Museum algorithm, but if A has 80 digits in it, you would need to make enough trials to match the number of atoms in the universe, which is apparently around 10 to the 80, right? So it's going to take longer than you're willing to wait, is the short answer, right? So what this means is that the nosy people, unless they're very, very, very keen, are not going to be able to figure out what A is. That's really good. So that's the idea. And in fact, interestingly, I said there is no way. Nobody knows if there is a way. All of modern e-commerce rests on a couple of unproven claims, namely that if you know A and you know, if you know n and you know n to the a, can you work out, if you know n and you know n to the a mod k, can you work out A? We believe that you cannot do so any faster than the British Museum algorithm, but maybe one of you will figure out how to do that, and then all of modern e-commerce will collapse. How's that for a challenge? Now, of course, people are worried about things like quantum computing, and indeed, the people who care about this are busy working out algorithms that will resist quantum computing. This one actually may not. But so there's movement in this space. But I think it's lovely that the bits, this bit stuff that I've been describing about, right in the space of a lecture that I hope is making sense to you. I can explain to you a problem that nobody knows the answer to, and yet which trillions of dollars depends on. Isn't that lovely? Isn't that wild? Okay. Now, episode 4. Wild bits. Now, we're moving on a bit in my life. This is me graduating from Cambridge in 1979. The picture is not terribly good because the photograph has degraded over time, and I'm not very good with pictures. This is my lovely parents and me with more hair than I have now. It was a very hairy era then. But I'd like to introduce you to another hairy person who taught me, John Horton Conway. So John actually gave me maths lectures. He lectured me on rings. He was a very eccentric and unusual Cambridge academic. He was he would come in bearing a sunflower and expatiate to us about the lovely Fibonacci series that you could figure out from its seeds. We had big blackboards which the mathematics lecturers would write on, and one of them was not movable. It simply went down to the floor. And John Conway would go all the way down to the floor. At the end of the lecture, he was lying on the ground, still speaking. Okay, so now, but he came up with, in 1970, he came up with something that's called John Conway's Game of Life. He always regretted that this is the main thing he's known for, because he was actually quite a good mathematician. But this is what he's known for, quite a bit, and I'm going to show you. Here it is. So it's played on a little grid of cells. So here are each of these little boxes is a cell that's either alive or dead. Right? It's one bit, like yellow is alive, black is dead. Now, and then there's a rule for how cells are born and die. So here is the rule. A cell with one or no neighbors dies from starvation. It's just too lonely. Right? A cell with 4 or more neighbors dies from overcrowding. By neighbors, I mean not just the ones up above and below, but the sort of diagonal left and right, but just the immediate closest neighbors. There are 8 of those, right? A cell with 2 or 3 neighbors that's already alive continues to be alive, and a cell that is not currently alive but has exactly 3 neighbors is born. All right, these are the rules of the game. That's it for the rules. Now, so let's see what happens. This is a, let's see, this is just a little pattern. I'm going to give you the link to this. Well, in fact, I already have it in the slides for the thing. And you just press go, and some kind of more or less mysterious things happen. Let's see, let me start again, reset. Stop. So there's something rather organic and unpredictable about what's going on. And then you wonder, might this thing stop ever? Could it grow without limit? Who knows what? So this particular one looks as if it's going on for quite a bit. Incidentally, this is not a special one. I just drew it randomly. And now it seems to settle down. Some of the bits don't change at all. They've all got exactly 2 neighbors. Some of them are flashing because they're getting born and dying. Now, you might ask some interesting, oh dear, come back. Where are we? Yes, here. So he came up with this when there were no computers. 1970, he did it on pencil paper. I don't know how he did it. 1974, computers started to come out. This was a mini computer, I think called a PDP-8. And this is John Conway with this vast screen here, had a huge cathode ray tube behind it. This is him playing the game of life on it. So this was 1974. This is 2 years before I arrived in Cambridge. So one of the things he wondered about was, do all the patterns die and get into a loop? I showed you one doing that. It got into a little loop or stable. And he thought probably not. Probably something could grow without limit. But he couldn't see how, so he offered a prize, $50, and Bill Gosper, another eccentric and remarkable US mathematician, won the prize the same year for this. I want to show you because it isn't so incredible. Where are we? Not that one. This one. Look at this. Okay, let me just set it off. This is called Bill Gosper's glider gun. I'm going to make it go a bit faster. You can do this yourself on your own computer. Look at that. Look at that. So there's something stable in the middle that is spitting out these little guys, and these little guys are called gliders. There's nothing, they're just following the rules, but it turns out that little pattern of cells, it doesn't get bigger, but it does move, right? Those gliders. So this glider gun is just indefinitely spitting out gliders forever. That was an amazing sort of revelation. So it means that this pattern will grow without limit. Okay, so that was that. Another good question is, can you predict, looking at a starting pattern, what it will do? Because after all, science is about predicting, modeling, figuring out what will happen in the future based on the answer. As far as anybody knows, no. Right? There really isn't a better way to figure out what the game of life will do other than just run it. That's a bit remarkable, right? It's sometimes called emergent behavior, when stuff happens that you can't quite predict. Stephen Wolfram calls it computational irreducibility, which is kind of a long word, but it's the same kind of thing. And incidentally, while I'm mentioning Stephen Wolfram, next time you're at Cambridge North Station, look at the facade. This facade is a cellular automaton picture. Right, just like the one I've shown you, not actually of the game of life, it's actually a Stephen Wolfram version of the game of life. He calls this one Rule 30. If you want to find out about that, read his book called, his doorstep book called A New Kind of Science. He's a very interesting, stimulating person. He was educated at Oxford. His mother was the terrifying philosophy tutor for my wife, Dorothy. So we had sort of multiple connections there. Okay, last interesting question about the game of life. Can these cells compute? Could we tame the wildness? What might that even mean? Oh, this is incredible. I'm going to just show you. So here is a picture of an Intel 4004. This is the very first microprocessor that came out, made by Intel in 1971. So by the time I was at school, these very first microprocessors were being available. And that was incredibly empowering to me as a teenager, because suddenly I could buy a chip. Here it is. You could plug it into a circuit board, you could wire it up, and it would be a computer. Very different from an IBM mainframe, which is all we previously had access to. So you're used to having phones and computers and so forth. So I can't tell you how exciting it was to be able to have your own computer back in the day. Now then, this Intel 4004, it had around 2,300 transistors, maybe 1,000 gates. I'll show you about gates. Modern microprocessors have 50 billion transistors. That is a lot more. Remember this thing about scale? Today it takes about so in 1971 it would take about a day to fly from here to Australia. If the improvement in air travel time had been the same as the improvement in the number of transistors, it would take 1/10 of a second to get to Australia. Right. This is a stupendous change. Anyway, that's by the by. Now, so what is inside the Intel 4004? It is a bunch of these gates. These guys are just back to George Boole, right? These are electrical circuits, these little things that look like aeroplanes here. They take two inputs on the left and produce one on the right. And so they're one of these. This is a NOR gate, and here's its little diagram, back to Mr. Boole, right? So if you have enough of these NOR gates, you can build a computer. So that's how computers are built. This particular circuit is called a full adder. Now, so maybe you could take the game of life, and you could think of that glider gun, those stream of gliders, think of that like a wire, and if there is a glider, that means 1, and if there's a little gap and no glider, that means 0. So you've now got all these wires, streams of gliders, 1s and 0s flowing along. Could you make gates, like OR gates and NAND gates and NOR gates and exclusive OR that combine them? Yes, you can. And I'm going to, am I going to show you? Yes. Here it is. This is a sort of rather zoomed out view of the game of life. You can barely see the individual cells. And this is a complete Intel 4004 implemented with glider guns. And see the little gliders? Those guys moving around are gliders. The thing in the corner that was reflecting the gliders is some complicated pattern that makes them bounce off at a right angle. And put the whole thing together, you've got enough gates to implement a whole 4004. So this thing can compute anything an Intel 4004 could compute, and an Intel 4004 can compute, well, anything. Don't you think that's amazing? Oh, look amazed. So I think it's just stupendous. Okay, so somehow we had this wild world of bits, rather uncontrollable, and we managed to tame it to be completely predictable and, in fact, implement a whole computer. The slides of this will be on, that we can put in links and show notes and everything, can't we? Yes, okay. Okay, that's it. That's rather, of course, it's a lot slower than an Intel 4004, really a lot slower, even on a modern computer. Okay. Final episode, bits that learn. So we're still sort of working bottom up. So this is a very different story. So here is something you might want to do with a computer, and we all want to do this. Make a computer recognize cats. I'm sure you've all tried to do this. So Magic Box is just some computer program. It takes a picture of a cat, all those pixels, lots of bits, just bits, and it's going to output one bit, yes or no, is this a cat? Right? How are you going to do that? Well, the standard way to do it, back in the day, in computer vision world, was to write complicated programs in conventional programming languages like Haskell or OCaml or Python or Java or Fortran or COBOL or something, and they use step-by-step algorithms. Do this and then do that, one thing at a time. They have data structures, they have loops and procedures, all of that, the stuff that you've learned on in conventional programming. Now, that works great if you're building a word processor or a video game, but it works very badly for recognizing cats, because what have you got to do? You've got to do, can I see little pointy ears? Can I see things that look like eyes? Do they have the right kind of relationship? It's all a mess. Very hard to do well. So here's the alternative approach that the machine learning community has told us about. We're going to instead have a very simple program. So there still is a program involved, but it's now a very simple one. This one is millions of lines long. This one is a few hundred lines long. But it is controlled by a lot of what they call weights. What is a weight? It is a number. Just a number. That's all. So 1 trillion numbers and a very simple program. So then what we're going to do is we're going to figure out, how do we figure out what the numbers are? Well, we're going to show this thing lots of cats and say, this is a cat. And we'll show it dogs and say, this is not a cat. And we'll try to adjust the numbers to make it recognize cats. Okay, we'll adjust those 1 trillion numbers. How are we going to do that? I'm going to show you, right? But the point is this at least is very, very different from the can you spot the pointy ears story. But I'm going to show you how to do this in the context of a much simpler example, which is a biscuit recognizer, a biscuit recipe recognizer. Imagine that I make biscuits. I'm not a very good cook. These biscuits consist only of flour, butter, and sugar. Nothing else, right? So they have X kilograms of flour, Y kilograms of butter, and the balance is sugar. Sorry, but it is. Right, so what I'm going to do is I'm going to, I want to say to this magic box, I want to say, if I use 0.2 kilograms of flour and 0.4 kilograms of butter, will I get a good biscuit? It's meant to say yes or no. All right? How do I do that? Well, one way to visualize this is to visualize it on a sort of scatter plot diagram, right? So imagine that I say the amount of flour is along the x-axis, the amount of butter is on the y-axis, and then I could bake lots of biscuits with different quantities. In the right hand, I put, so flour 0.2 and 0.5, and then I feed that to my children, and they say, Dad, bad biscuit. Right? So then I try 0.1 and 0.5, and they say, Dad, great biscuit. Right? So I just make a big table like this. I have to bake. I do a lot of baking, and I plot the results on here. Right? So the blue ones are the good biscuits. The orange ones are the bad biscuits. Right? And so now we say, oh, how could I, as it were, separate these two groups? Well, I could separate them like this. I could put a line that separates them. Now, things below the line, when I've got a new xy, I say, what about 0.25, 0.7? Then I say, well, is 0.25, 0.7 above the line or below the line? Below the line, bad biscuit. Above the line, good biscuit. Easy, right? What could be hard about this? Well, as we all know, lines are defined. GCSE mathematics, lines are defined by a linear equation. Here it is, ax plus by plus c equals 0, where a, b, and c are some magic numbers. These are the weights, right? And so above the line, if I look at an xy point that is to the right, then ax plus by plus c will be bigger than 0. And if I look at an xy point to the left, then for the bad biscuits, ax plus by plus c will be less than 0. So what does that means is that my magic box simply computes ax plus by plus c, given x and y, that is the amount of flour and sugar flour and butter I'm going to put in, and given the weights a, b, and c, which I still have yet to figure out. And then it just says, if it's positive, good biscuit. If it's negative, bad biscuit. That's my whole AI system, all right? All right. So pretty simple, really. Well, how could I do that? Well, the thing is, I need to work out A, B, and C. How do I do that? Well, here's a good way to do it. Try a random A, B, and C. Here's one I've drawn. Now pick a biscuit that is mispredicted, right? One of those good biscuits that says it's bad, right? Now tug the line a little bit towards it. Just a little bit, right? By changing A, B, and C a little bit. And now do that again and again and again. Do it a bazillion times. Gradually the line sort of drifts around until it is between the biscuits. And that is called learning or trading. So now you know that is all that is happening. They're just tugging lines around. But they show it some training data. They say, does it give the right answer? If not, I'll do a little bit of tugging. Now, I'm not going to describe exactly how to do the tugging, but it has a long name. It's called back propagation. It's a good way to impress your friends at parties. But I am going to show you how it happens in practice using this rather lovely website called TensorFlow Playground. So here it is. So here I got my that little box in the middle. That was my ax plus by plus c box. And here I've got my data spread out. And when I press the little play button up here, the little triangle, it's going to run that repeatedly, pick a mispredicted biscuit, and tug. And lo, it finds a line between them. And I can sort of reset it and find another one. Well, you think, that's not so hard. Is that really all there is to machine learning? Well, not quite. So suppose it wasn't quite as easy as that. Suppose it was like this. Oh. Now there isn't really a line that will do the job, is there? What are we going to do? Oh, I know. We could have many little lines and somehow get them to vote. Right, so maybe if we have more lines, look, let's this thing lets you hidden layers. They're called hidden layers. Sounds expensive, doesn't it? Or complicated. But look, let me try doing this, and then let's try adding some, more in each layer. I don't know. There's a lot of suck it and see in AI. There we go. Let's see about that. So now, one set of ax plus by plus c's is feeding the next set of ax plus by, which is feeding the next set. So of course I've got a lot more a's, b's, and c's. Each of these boxes has 3 numbers, right, that I've got to learn. But now look, what happens? Whoa! Don't you think that's spooky? And I tell you, all I have done is ax plus by plus c. There's a little bit of nonlinearity I haven't told you about, but don't worry about it. But really, it's basically ax plus by plus c, just arithmetic, and that tugging business, which is also just a bit more arithmetic. It's kind of amazing. Then, look, you might think, what about more complicated things like this? Oh, this is such fun to play with. You should all get a hold of this and give it a try. Ooh, it's really trying. Maybe it would work better if I gave it a bit more neurons to work with. Who knows? Let's have another go. Oh, ooh. And you can have a lot of fun playing with this. It can even get a bit harder. There's a little data set here that's really quite a bit harder. How do you separate those guys? Right. Oh, maybe you can do this yourselves. I mean, you could probably do it before the end of this talk just by having a little play. Look. And so it has a fairly decent stab. Actually, even with this spiral one, it does a reasonably good job after a while. Okay. End of story. Have a go with this TensorFlow program. It's a lot of fun. And it is showing you exactly what is really happening in neural networks. This is what AI does. ChatGPT is exactly what I have shown you, but instead of half a dozen little boxes, it has nearly 1 trillion little boxes. That is a lot. Scale matters. Remember? So how does ChatGPT really work? The same thing at much larger scale, but there is a little feedback loop. So with ChatGPT, you put in your question, and it simply predicts the first word that it will say, like the. It says, that's a high probability output for my first word. Then it feeds that back to the input, right? So it knows what it has said so far. And then it says, maybe I can predict what is the most statistically likely thing that I might say next, based on all of the weights that I've learned. And then it predicts one more word. So each time, it predicts one more word each time based on what you asked it and what it has said so far. And that is all. I mean, I'm simplifying a little bit. I mean, there's like gazillions of people working in AI, and it's incredibly clever, and they are brilliant, brilliant people. But at its roots, it's just the biscuit predictor. At its roots, that's all that's going on. ChatGPT is just 1 trillion floating point weights and a lot of arithmetic. Now, before we get too excited about this, let's just go back to George Boole, right? So we've gone all the way from Boolean circuits up right up to ChatGPT. And there's George Boole married a woman called Mary Everest Boole. She was a niece of Sir George Everest, who actually was the person who named Mount Everest. But she wrote some lovely books called, I love this title, The Philosophy and Fun of Algebra and Logic Taught by Love. Oh, I wish I'd written a book with that name. Now, they had 5 rather clever daughters, but they also had a great-great-grandson from one of those daughters, who is Geoff Hinton, FRS, who was educated at Cambridge and got the 2024 Nobel Prize for neural networks. He was doing this neural network stuff back in the day when the scale was not enough to do anything very useful, right? So people were saying, Geoff, it'll never work. But he stuck to it. He stuck to it for a long time, and sure enough, it works at scale. So he is, as it were, one of the fathers of modern AI. I'm very pleased that he got the Nobel Prize, and also that he was educated here at Cambridge, well, and Edinburgh as well, must be said, his PhD there. But I love the fact that he is the great-great-grandson of George Boole. So the two ends of our story are connected by blood. Okay, now, little bit just to finish up here. So then, so this AI stuff, well, we all know it's not, I think we all know now that it's not just a fad. This is going to make a difference to all of our lives, right? New opportunities, right, to automate away meaningless toil. And that can be really quite a big deal. I mean, this isn't just a toil like plowing fields, but this is toil like looking at X-rays to look for cancers. If you can do that 1 million times faster and focus the human being's attention on the dodgy ones, like we really need that judgment, that's much better than taking highly qualified people and getting to look at lots of really boring X-rays. So it's a zillion things that AI could do. That's fantastic, right? But there are also some genuinely new risks, right? So many of you will know about this. How do we even know what's true anymore? Maybe the photographs that I've shown you were all made up by ChatGPT or some variant Anthropic or stable diffusion. No, they were actually all real, but I've only, you've just got to believe me. So somehow we need good judgment about how to deal with all this AI stuff. And I think good judgment is rooted in understanding, right? And some visceral knowledge that I hope maybe even you will have got from today is quite helpful. Let me give you some examples. Right, so you may have heard about what is the problem with biased data or unrepresentative data in AI. Well, based on what I've shown you already, you can see it. It's plain as a pikestaff. If I ask, is this a good biscuit, this XY point, is that going to be a good biscuit or a bad biscuit, or even out here? How would I know? Maybe all the good biscuits really are in the top right-hand corner, and all of the rest of this is bad. But I have no data there. So I can deduce little or nothing. I'm just generalizing in a space that I really don't know very much about. That's not good, right? And so, this is, there are celebrated examples of AI systems giving very wonky answers because, and in places that matter, right, like, are we going to give you an insurance policy or are we going to let you interact? This matters, right? So the data that you train on matters a lot, and if you have unrepresentative data, it really doesn't work. Here's another thing that goes wrong. We talked about emergent behavior. There's quite a lot of emergent behavior in these AI systems. ChatGPT 3, it turned out, couldn't really do arithmetic to begin with. You'd ask it, what is 4 plus 99? And it would confidently say 1,075. But of course, remember, it's always going to confidently say something. That's why we call them hallucinations. Is it above the line or below the line? Say something. But it turns out, when it hit 1.3 billion weights, parameters, floating point numbers, whoa, it suddenly got rather good at arithmetic. Nobody knew that 1.3 billion was going to be the knee, or even that there would be a knee, but there was. That's emergent behavior. It's very difficult to predict. Very difficult to predict. So there's sort of something, it's a bit like the game of life stuff. We don't quite know what's going to happen. So here's another example of thing you might wonder about. Big AI models, large language models, have now essentially consumed all of the human-generated internet, all of it. They have no new data to go on. So what's going to happen now? Oh dear, they're going to start consuming their own output, particularly as the internet is increasingly full of the output of AIs, and we can't tell the difference very easily between the output of AIs and human-generated stuff. So AI is going to be learning from themselves. And if you just feed on your own dog food, right, you can imagine that eventually bad things are likely to happen. And so let me just give a little moment of recollection for our friend and colleague Ross Anderson, a professor in the computer science department here at Cambridge who died just last year. And one of his last papers was about, it's called model collapse, this thing, when they just become completely hopeless because they've been trained on the data. When trained on recursively generated data, the recursive means it's the output of some other AI or even of itself. Right? So, but what I'm hoping is that some elementary understanding of how the thing works leaves us in a position where we can at least ask these questions, right? And make sort of intelligent, well-judged judgments about what we want AI to do for us. Okay, so I'm going to conclude because we are coming up on the hour. Very good. And so I just want to come back to the title, Bits with Soul. All right, so this is the last bit of my story arc here. Now, you might have been thinking, Simon's going to say that bits have soul, but actually I want to say bits do not have souls. Right? ChatGPT is literally 1 trillion floating point numbers and a lot of arithmetic. How could that possibly have a personality or feelings? Right? Well, we get into philosophy here. Maybe we are just lots of floating point numbers and arithmetic. But to me, it seems like knowing that that is all that is happening, there's no more mysterious magic. It's just ax plus by plus c and some nonlinearity and a lot of numbers that helps you have a more sort of, well-grounded relationship with these large language models. So I don't think they have souls or personalities, but nevertheless, they are changing our world in quite profound ways. So what does that mean we should do? Well, the bits may not have souls, but we do. All right? So this bits at scale, whether it's AI or just computers generally, enormously amplify what we can do. Right? They don't limit our creativity, they expand our creativity. They expand what we can do and they expand the opportunities for us as individuals, I think. But they do deeply affect our personal lives, and you might think about stuff like privacy and whether you'll have a job, right, in the world of AIs, and our collective lives. You might wonder about free speech and polarization and deepfakes and even the future of democracy, right? There's a lot going on here. So what does that mean? That means that for the safety of our souls, I think we all need to be engaged, right? We need to not just say, well, I'm not clever enough for this, I'm going to let the people in white coats sort it out, right? This is something that concerns all of us. So I put here, heart and soul, we just need to, all of us, play some kind of role in the conversation about what digital technology, most topically AI, it wants to play in our society. But in particular, I think our young people need a solid foundational understanding of some of the underlying principles that I've been describing today, right? They need to know, I think, about bits. So I'm talking about information, computation, communication. That's what I would call computer science, right? Computer science is a scary way to say it, but that's really all it is. And so just as we teach our children the foundational principles of natural science, of physics, of chemistry and biology, not because they're all going to become physicists or biologists, but because they need some understanding of the natural world that surrounds them in order to make good judgments about their lives, right? How can you think about global warming or atmospheric pollution if you know nothing about physics or chemistry at all, right? You don't need a deep, big, PhD level understanding, just some elementary grounding. That's what we want to do, I think, for computing. And so now I see very much computer science as sitting alongside maths and natural science as being the foundational stuff that every child needs to learn a bit, so that they can do these things. Have agency. I really like the word agency. I want our young people to be the masters of technology, not the slaves. And that means that they need to be active agents in the world, not passive recipients. I want them to have well-informed judgments, and I want them to have lots of fun. And I do want them to get to have good jobs and to make the world a better place. So let me just mention Computing at School is the organization. This is back to a little personal thing. Here at Cambridge in 2007, we founded this organization, Computing at School. Alan's been quite involved in various ways as well. Lots of people in this room have. This is about reimagining what education might look like as a school, what computing education might look like as a school subject. How do we teach computer science to our children? So alive and strong, and indeed we have quite a big effect on the national curriculum for computing already, so that's really good. So I just want to finish with this picture. Right, this is what I want to happen for our children, and I'll thank you very much.
Thank you so much, Simon. You began this lecture with 3 words: joy, elegance, and beauty. And that was the most joyful, elegant, and beautiful lecture I have heard for a long time. It was also exciting, inspiring, informative, and clarified for me a great deal about computer science, but also highly entertaining. So thank you very much indeed for getting this series off to such a wonderful start. Do please come back, especially you, Simon, but everybody else as well, for next week's lecture, which is given by the musician and composer Maya Yosef, who will be talking on the power of music, a journey back in time, when you can expect both music and words as part of her performance. But please, before you go, just join me once again in saying an enormous thank you to Simon. I would say thank goodness for you and thank goodness for Computing at School. So thank you very much.